Usually when we talk about rendering a surface in a video game or just any 3D simulation, there's this underlying assumption of permanence.
Oh, absolutely. Like you build a stone wall in your software,
Yeah,
right?
exactly.
Sure.
You establish the geometry, and it just stays a wall. You map a nice high-resolution brick texture to it, you bake in your lighting, and the graphics card just draws it.
Right. It's fundamentally static.
Right. It's predictable geometry doing very predictable things.
It's entirely finite. I mean, from a computational perspective, the GPU knows exactly where those vertices are going to be from one frame to the next. The transformations are just linear.
But the second you step into the world of rendering ocean water,
Yeah.
all of that predictability just shatters.
Oh, yeah. It goes completely out the window.
You're no longer dealing with a surface. We are looking at a rendering landscape that is, quite frankly, terrifyingly complex, especially if you're tasked with building it from scratch.
Because you're stepping away from drawing a shape, right? And you're stepping into simulating a chaotic, light-bending fluid. It's like the absolute definition of computational muddy waters.
Which is precisely the labyrinth we are navigating today. We're going to completely deconstruct the math, the physics, and the modern web GPU programming techniques you need to build a photorealistic, interactive ocean simulation from absolute scratch.
It's a massive undertaking.
It really is. And before we get into the weeds, I want to send a very specific shout out to the computer science scholars tuning in today. The Bus and Sigma scholars of Edward Little High.
Yes! Awesome to have you all here.
We know you guys are tackling some incredibly ambitious rendering projects right now, so this deep dive is custom tailored to help you tear apart the mathematics and the shader pipelines you're going to need.
And it's a phenomenal mission for you to undertake. Because a convincing ocean is not just some, flat, scrolling blue plane with a normal map slapped on top.
No, definitely not.
To make it behave like an actual body of water, to give it that sense of weight and physical threat, it requires some incredibly heavy mathematics and massive computational power.
To guide us through all this, we've got a towering stack of sources today. We are unpacking Jerry Tessendorf's seminal paper on simulating ocean water, which fundamentally changed how graphics programmers approach this whole problem.
A total game changer, that paper.
We're also cross-referencing that with Chapter 18 of GPU Gems 2, which focuses on vertex texture displacement. And we're digging into some highly detailed tutorials from Barth Cave on WebGPU and WGSL.
Right, getting into the actual card.
Exactly. And we're bringing it all together with modern implementation case studies, specifically Youngsu's incredible WebGPU port of classic water simulations.
And we should probably set expectations right up front here. We are not just going to make a wavy surface today.
No, we're going way deeper.
By the end of this deep dive, you're going to understand how to leverage fast Fourier transforms, how to structure modern compute shaders, and how to use the Jacobian determinant to mathematically simulate truly chaotic storms.
And dynamic foam, floating boats, realistic underwater caustics. The works.
All of it.
Let's start at the foundation, though. Before we could even think about writing a line of WGSL code, we need to know how to actually move a single vertex in a way that looks like a wave.
Right. Back to basics.
If we look back at the early days of computer graphics, how did pioneers first approach this problem of moving water?
Well, to truly understand the origin of water simulation, we actually have to look past the birth of computer graphics entirely.
Wait, really? How far back are we talking?
We have to go back to the realm of classical physics in 1802.
1802. So we are talking about the era of quill pens and parchment, way before anyone even conceptualized a programmable pixel.
Precisely. We're talking about a Bohemian physicist and engineer named František Josef Gerstner.
Okay, Gerstner.
He was grappling with fluid dynamics, specifically trying to find an exact solution to the Euler equations for surface gravity waves.
Let me pause you right there, because the Euler equations get thrown around a lot in physics discussions, often without much context.
Oh, for sure.
If I remember correctly, these equations treat fluids as a continuous field, rather than trying to calculate the bouncing of individual microscopic water molecules, right?
That is spot on. Tracking individual molecules is computationally impossible even today, let alone in 1802.
Yeah, you need a supercomputer just for a drop of water.
Exactly. So the Euler equations allow us to look at a fluid as a continuous substance. It tracks the conservation of mass and momentum across a defined space. Gerstner was trying to find a mathematical model that satisfied these equations specifically for the surface of deep water.
And did you find it?
He did. He found a solution that describes periodic waves where the actual fluid particles don't just bob straight up and down, they move in uniform circles.
I want to visualize this. If I drop a rubber duck into the ocean and a massive swell passes underneath it, you're saying the duck is not just traveling on a vertical y-axis elevator.
No, it's not. As the wave approaches, the water actually pushes the duck forward and upward toward the crest.
Oh, I see.
Then, as the crest passes, the duck slides down the back of the wave and is pulled backward into the trough. It traces a complete, uniform circle in physical space.
So it's essentially functioning like a car on a Ferris wheel.
Yes, that's a great way to put it.
The car itself is rotating in place, but because it's attached to this larger moving system, the shape it traces out on the top half of the rotation is very different from the bottom half.
Exactly.
At top of the wave, the crest would bunch up and form a sharper peak, while the bottom of the motion stretches out into a wide, flat trough.
That Ferris wheel visualization maps perfectly to the geometry. Mathematically, the shape that the circular particle motion creates on the surface of the water is called an inverted trochoid.
An inverted trochoid, okay.
And for a very long time in early computer graphics, this Gerstner wave, this inverted trochoid, was the absolute gold standard for rendering water.
Really? How would they use it?
Programmers would take a flat grid of vertices and apply this math. They might stack 3 or 4 of these Gerstner waves together, having them cross at slightly different angles and speeds to create a fluctuating surface.
But there has to be a glaring limitation there. I mean, if I am building a simulation of a hurricane in the middle of the Atlantic, stacking a few perfectly symmetrical Ferris wheel motions together is not going to look like a chaotic, life-threatening storm.
No, it looks entirely synthetic.
Yeah, I imagine so.
Gerstner waves are fantastic if your goal is to render a stylized repeating swell, like perhaps a calm day at a sheltered beach. But actual oceans are governed by chaos.
Right. Wind, weather, currents.
Exactly. They are driven by massive, unpredictable wind patterns sweeping over hundreds of miles of open water. Stacking a few mathematically perfect trochoids simply looks too uniform. It completely lacks the grit and the infinite variation of nature.
So the fundamental problem shifts from geometry to variety. How do we break that mathematical uniformity? How do we inject that natural wind-driven chaos into a flat grid of vertices?
This is where we reach the statistical revolution in computer graphics, which was pioneered by Jerry Tessendorf.
Ah, the paper we mentioned in the sources.
Yes. He published a paper that fundamentally argued against trying to track individual particles or use perfectly defined geometric shapes like Gerstner waves.
So he threw out the geometric approach entirely.
Basically, yeah. He realized that to make water look real, we needed to abandon explicit geometry and embrace statistical models based on actual real-world oceanographic data.
Moving from geometry to statistics. That implies we are no longer saying draw a wave here. We are saying what is the probability of a wave existing here?
Exactly. For decades, oceanographers had been out on the water, taking meticulous measurements of ocean surface elevation under various wind conditions.
Just sitting out there in boats, measuring waves.
Yep. They dropped buoys, used radar, and gathered massive data sets on how wind creates waves. Tessendorf took this empirical data and applied it to computer graphics using something called the Phillips spectrum.
Okay, for the scholars taking notes on this, we need to carefully break down the math of this Phillips spectrum. We can't just read the raw algebra over the microphone, because that is impossible to visualize.
Fair point.
Conceptually, what is this formula actually calculating?
At its core, the Phillips spectrum calculates the energy, or basically the height, of a specific wave based on the wind blowing across the water. It's a probability distribution.
Okay.
It looks at a wave's length and the direction it wants to travel, and it compares that to the wind.
Let's look at the levers a game developer actually pulls when they implement this. If I'm in my shader code, I see an amplitude factor, usually labeled A. I assume that's essentially the master volume knob for the entire ocean.
That is your global scale. You increase A, the waves get taller across the board. You also have a parameter L, which represents the size of the ocean pile you are generating.
Like maybe a patch of water 1,000 meters across.
Right. But the most critical parameters are the vectors. W for the wind and K for the wave vector.
The wind vector W makes sense. It has a direction, like northeast, and a magnitude, like 40 knots. But what exactly is the wave vector K representing?
K represents the specific wave frequency and direction we are evaluating at that exact moment in the calculation.
Got it.
You have to remember, the ocean is made up of millions of overlapping waves of all different sizes traveling in all different directions. The formula evaluates them one by one, and to do that, it uses a dot product between the wave direction K and the wind direction W.
The dot product. Okay, this is where the math physically connects to the natural world. If I recall my vector math, the dot product is a measure of how closely aligned two arrows are.
Precisely. The formula specifically takes the absolute value of the dot product of the wave vector and the wind vector and it squares it. This is the mathematical engine of the Phillips spectrum.
So what happens when they align perfectly?
If a specific wave k is trying to travel in the exact same direction as the wind w, the vectors are parallel. Their dot product is 1. The formula gives that wave maximum energy.
And if a wave is trying to travel perpendicular to the wind, like say the wind is blowing north, but the math is evaluating a wave trying to travel east.
The dot product of perpendicular vectors is 0.
Oh, wow.
Yeah, so the formula completely suppresses that wave, it zeroes it out. This beautifully mathematically ensures that your simulated ocean naturally develops those long, sweeping wind lanes. Waves that fight the wind are destroyed, waves that ride the wind are amplified.
But I see a contradiction here. If the Phillips spectrum is just a mathematical formula based on wind direction, isn't it still going to output a perfectly smooth, idealized representation of a windblown sea?
It is, yeah.
Because it's a probability curve, it lacks the microscopic chaos we talked about earlier. Where does the grit actually come from?
You've identified the exact gap in the base formula. The spectrum alone is too perfect. It represents the average state of the ocean under those wind conditions.
So how do we mess it up?
To make it look like a specific real moment in time, Tessendorf's method requires us to multiply this perfect statistical spectrum by complex Gaussian noise.
Complex Gaussian noise, meaning we're injecting a carefully controlled layer of random numbers into the foundation of the math.
Essentially, yes. We generate random numbers that have a mean of 0 and a variance of 1. By taking our idealized statistical spectrum and multiplying it by this noise, we give the ocean its chaotic fingerprint.
It makes it unique.
Exactly. It guarantees that even if two swells have the exact same underlying frequency and wind energy, they will never look identical. The noise roughs up the surface, providing the microscopic jitter and variation that our brains instantly recognize as organic nature.
Okay, so now we have this incredibly detailed, chaotic, wind-driven mathematical model. We have our Phillips spectrum multiplied by Gaussian noise. We've defined our wind direction and our global amplitude. Yeah. But it is completely static.
Right, it doesn't move yet.
We've essentially just generated a very complicated, highly detailed, lumpy photograph of an ocean. How do we actually make this massive mathematical structure move over time?
That is the next monumental hurdle. To animate a statistical model, we have to look at the underlying physics of how waves propagate through a medium. This propagation is governed by something called the dispersion relation.
I want to dissect that term. In optics, dispersion is what a prism does to white light, right? It separates the light into a rainbow because different colors, different wavelengths bend at different speeds. Does dispersion mean the same thing in fluid dynamics?
The underlying concept is identical. In fluid dynamics, the dispersion relation dictates that waves of different lengths travel at different speeds.
Oh, interesting.
For an ocean of deep water, the formula is remarkably elegant. The square of the frequency is equal to gravity multiplied by the magnitude of the wave vector.
Which means the speed of the wave is dictated entirely by its wavelength and the gravity of the planet it is on.
Exactly. Long waves, those massive wide swells, travel significantly faster than short, choppy waves. This is a physical reality you can observe.
Really? How so?
If a massive storm system forms hundreds of miles out at sea, it generates a chaotic mix of all wave sizes. But because of the dispersion relation, the long, fast swells separate from the short, slow chop.
Oh, wow. I never realized that.
Yeah, those long swells will actually outrun the storm entirely and begin crashing on the shoreline days before the actual storm clouds arrive.
Go.
The math models this physical separation perfectly.
That is fascinating. The ocean is naturally sorting itself by wavelength as the energy travels. But what happens when that energy finally reaches the shoreline? The water is no longer deep. Does the dispersion relation break down?
It doesn't break down, but it adapts. If the water becomes shallow, we introduce a new variable for depth. Let's call it d.
Okay.
The formula expands to include a hyperbolic tangent function applied to the depth and the wavelengths.
A hyperbolic tangent. If I try to visualize that curve, it approaches a limit. How does that mathematically alter the physical wave?
As the depth d gets smaller and smaller near the shore, that hyperbolic tangent term acts like a massive brake pedal on the wave's speed. The wave is physically feeling the drag of the ocean floor.
And because the front of the wave hits the shallow water first and slows down, while the back of the wave is still in slightly deeper water moving fast, the wave bunches up.
Exactly. It compresses horizontally, which forces it to grow taller vertically until it finally becomes unstable and crashes on the beach.
That makes total physical sense.
Yeah.
So we have our initial static spectrum, our photograph, and we now have the dispersion relation, which is a rule book telling us exactly how fast every single wave frequency in that photograph should be moving.
Right. We have the pieces.
How do we actually combine those two things in code to get a frame of animation at a specific time, say time t?
We calculate what is called the time-dependent spectrum. We take the initial static spectrum we built, and we use Euler's formula, specifically involving the exponential of the complex number d, the frequency, and time t.
That sounds heavy.
It mathematically advances the phase of every single wave based on how much time has passed. We also have to factor in the complex conjugate of the initial spectrum with a negative time phase.
Wait, why the negative time phase? That sounds counterintuitive.
It ensures our math produces real, propagating physical waves that travel across the surface, rather than just creating standing waves that bob up and down in place without going anywhere. It's a mathematical necessity to maintain the illusion of forward momentum.
I am looking at the sheer volume of calculation required here, and I am hitting a mental roadblock regarding performance.
Let me guess. The nested loops.
Yes. To get the final height of the water at any specific vertex on our grid, we have to add up the results of this time-dependent spectrum for every single wave frequency. If our ocean grid is 512 by 512 vertices, that's over 260,000 individual grid points.
Yeah, it's a lot.
And for every single one of those 260,000 points, we have to calculate and sum up thousands of individual sine and cosine waves. That is, hundreds of millions of complex floating point multiplications per frame. How does a computer not instantly lock up trying to run that at 60 frames per second?
Well, if a programmer attempted to do this the naive way, literally writing a loop that calculates every single sum individually for every vertex, the application would absolutely lock up.
It would just melt the CPU.
Pretty much. In computer science terms, that approach has a time complexity of O(n) squared. As you increase the detail of your ocean grid, the computational cost explodes exponentially. It is practically impossible for real-time rendering.
So how is it possible that I can boot up a game on a standard console and see this massive rolling ocean running effortlessly?
Because we rely on what is widely considered one of the most important algorithms of the 20th century, the fast Fourier transform, or FFT.
The FFT. I have seen this acronym in signal processing and image compression and now in fluid dynamics. I feel like this is the engine of the entire modern digital world.
It truly is. The FFT allows us to compute all of those millions of overlapping sums simultaneously. We have our time-dependent spectrum, which currently exists in the frequency domain.
Frequency domain. So it's basically just a massive list of wave frequencies, amplitudes, and phase shifts.
Exactly. It's a list. The FFT algorithm takes that list and transforms it back into the spatial domain.
Meaning it converts a list of frequencies into a physical picture, a height map.
Yes, it spits out a 2D image, a texture, where the brightness of each pixel represents the exact vertical height of the water at that specific spot on the grid.
That's incredible.
And the brilliance of the Cooley-Tukey FFT algorithm is that it recursively breaks down the math, reducing the time complexity from O(n) squared to O(n) log n. It turns an impossible calculation into a trivial one.
Let me try to map this to something I am very familiar with, audio engineering.
Oh, that's a perfect parallel. Go ahead.
If I am sitting in a digital audio workstation, a DAW, I might have a massive music project open. I have hundreds of individual instrument tracks, drums, bass, synths, vocals. Each track is essentially its own complex waveform with its own frequencies and amplitudes.
That is very accurate.
If the computer had to manually figure out the final volume of the speakers at every single millisecond by reading every single track one by one, playback would stutter and fail.
Right, the CPU couldn't handle it.
But the FFT is like hitting the export button. It takes all of those independent overlapping frequencies and instantly mixes them down into a single cohesive MP3 file. In our case, the MP3 file is the height map texture. It consolidates the chaos into a single usable asset in a fraction of a second.
That is exactly what is happening under the hood. It's a mathematical mixdown, and because the algorithm is so elegantly efficient, modern GPUs can run this entire process, generating the time-dependent spectrum and mixing it down via the FFT completely in real time, every single frame without dropping a single bead of sweat.
I followed the logic perfectly. We take this height map texture that the FFT spits out, we sample it in our vertex shader, and we move the vertices of our grid up and down on the y-axis.
Yeah, that's the basic displacement.
But wait, I see a massive visual problem here. If we are only moving the vertices straight up and straight down based on this height map, aren't we just going right back to the Ferris wheel problem we had with the Gerstner waves in 1802? The peaks of the waves are going to look very round and soft.
You have identified the exact limitation of purely vertical displacement. If you stop the simulation here, your ocean looks like a lumpy, rolling blue carpet.
A rolling blue carpet, not very threatening.
Right. It has the right frequencies, but it completely lacks the sharp, aggressive, stormy peaks that make a real ocean look dangerous. A real wave does not just lift water, it pushes it forward.
So we're not just moving vertices vertically, we have to pull them sideways. How do we compute that horizontal shift without destroying the FFT we just built?
We don't destroy it, we duplicate the process. We actually have to run a second inverse FFT calculation.
A second one. So we are mixing down another entire track.
Yes, but the second FFT is specifically engineered for horizontal displacement. We go back to our time-dependent spectrum in the frequency domain, but before we run the mixdown, we modify the formula.
How so?
We multiply the spectrum by -I times the wave vector k divided by the absolute magnitude of k.
Okay, let's translate that algebra into physical geometry. What is that modification actually doing to the grid of vertices?
It's calculating how much each vertex should be pulled horizontally toward the crest of the nearest wave. I want you to imagine a large, flat sheet of highly elastic rubber.
All right, I had the rubber sheet in my head.
If you take a baseball bat and push up from underneath the sheet, you create a wave. The rubber stretches evenly in all directions to accommodate the new height. The peak is perfectly round. This is vertical displacement.
But the ocean is not made of rubber.
Exactly. Now imagine you push up with the bat, but you also reach down and pinch the surface of the rubber, pulling the surrounding material inward toward the very tip of the bat.
The peak of the wave would become incredibly sharp, almost like a spike. And the area around it, the valley or the trough of the wave, would be stretched out and become very flat because all the material was pulled toward the peak.
That is exactly what the second FFT does to the vertices. It pinches them horizontally at the crests. It completely changes the silhouette of the water. The round, fair weather swells transform into aggressive, leaning, choppy peaks. It looks genuinely turbulent.
But this introduces a massive design paradox. If we are mathematically pinching these vertices together at the crests of the waves to make them sharp, what happens if we pinch them too much?
That's a great question.
In a real ocean, if a wave gets too sharp and too steep, gravity takes over. The wave breaks. It crashes down on itself and spawns whitecap foam. How do we tell our WebGPU simulation when to draw foam? We can't just guess.
We don't have to guess. The math provides a built-in, elegant trigger, and it relies on a concept from vector calculus called the Jacobian determinant.
Let's unpack the Jacobian. I know a determinant in linear algebra is usually a measure of how a matrix scales an area or a volume. If a determinant is 2, the area doubled.
You're right on the money. In this context, the Jacobian determinant, let's call it J, is continuously measuring the physical area of the water surface as we apply our horizontal displacements.
So it's tracking the stretch.
Yes. The formula involves the partial derivatives of our displacement fields. It tracks how the x position changes relative to the original grid, combined with how the z position changes.
So as our second FFT pulls the vertices horizontally toward the peak of the wave, the physical area of the geometry at that peak is shrinking. The determinant is getting smaller.
Yes. The math is tracking the squishing of the space.
And what happens if the wave is so aggressive that the vertices are pulled so far they actually cross over each other? The geometry folds inside out.
That is the magic threshold. When the vertices cross over, the wave has physically folded over on itself. And mathematically, the area essentially becomes negative. The value of the Jacobian determinant drops below 0. J becomes less than 0.
Wait, so a negative Jacobian determinant literally means the math has detected a breaking wave.
Precisely. It is a flawless, mathematically derived trigger.
That's wild.
As a graphics programmer, you don't have to write a complex physics simulation to track the momentum of the water to guess where the foam should appear. You simply write a rule in your fragment shader. If the Jacobian J at this pixel is less than 0, blend in the white foam texture.
It just happens automatically.
The math dynamically and automatically spawns foam exactly at the peaks of the most chaotic, violently breaking waves.
I love when the raw mathematics inadvertently solve an artistic rendering problem. It's a beautiful intersection of physics and procedural art.
It's one of the most satisfying moments in graphics programming, seeing that foam dynamically appear based purely on the calculus of the displacement.
All right, we have constructed a monumental theoretical foundation here. We have the Phillips spectrum for wind statistics, the dispersion relation for speed, the FFT for real-time calculation, horizontal displacement for choppiness, and the Jacobian for foam.
It's a lot of theory.
But theory only goes so far. We need to pivot to the metal. How do the scholars at Edward Little High actually code this today? Because nobody's doing these hundreds of millions of calculations in C++ on a single-threaded CPU anymore.
Absolutely not. The CPU is far too slow and too sequential for this kind of massive parallel processing. To run an FFT on 260,000 vertices 60 times a second, we must use the GPU.
Right?
And if you are building this for the modern web, the standard API is WebGPU.
Let's talk about that shift. WebGPU is actively replacing WebGL. For a long time, WebGL was the undisputed king of browser graphics. Why abandon it? What was the fundamental flaw in WebGL that necessitated a completely new API?
WebGL was a phenomenal achievement, but we have to remember its lineage. It was essentially based on OpenGL ES, which is a much older state machine-based architecture.
A state machine, meaning the graphics card acts like a giant room with thousands of light switches. You flip a switch to bind a texture, you flip another to set a blend mode, and you hope that by the time you issue the draw call, all the switches are in the right position.
Exactly. It involved a massive, invisible global state. And for complex computational simulations like an ocean, WebGL required a lot of hacky workarounds.
Like what?
For instance, our complex time-dependent spectrum data requires high precision. We can't store that in a standard 8-bit image file. We needed floating point textures.
Oh, right.
In WebGL, that meant requesting specific extensions from the browser, like OE's texture float, and just crossing your fingers that the user's specific mobile phone GPU driver actually supported it.
I remember the nightmare of debugging WebGL extensions. Half the time, the simulation would just fail silently on certain hardware.
WebGPU strips all of that away. It brings explicit state management and immutable pipeline objects. It natively supports advanced features like compute shaders and floating point storage out of the box.
It's just built in.
Exactly, aligning the web browser closely with modern, low-overhead desktop graphics APIs like Vulkan, Apple's Metal, and Direct3D 12.
So WebGPU is this shiny, incredibly powerful new engine, but to actually command it, we have to write our logic in a completely new shading language.
Yeah.
WGSL, WebGPU Shader Language. Now, I have looked at the code structure from Barth Cave's tutorials, and coming from JavaScript or even standard GLSL, WGSL looks violently strict.
It is intentionally strict, and there's a very deep hardware reason for that.
Break that down for me. Why does the language need to be so punishingly explicit?
Think about how a GPU physically works at the silicon level.
Yeah.
You have thousands of individual compute cores trying to access memory simultaneously.
Right.
In the old WebGL days, you would bind a texture to the global state, and the shader would just sort of reach out into the ether and grab it. The GPU driver had to constantly guess your intentions and manage memory on the fly.
Which is slow.
Very slow. It led to pipeline stalls and massive CPU overhead.
So WGSL forces you to do the driver's job for it.
It forces you to declare your memory layout perfectly up front. You'll notice in WGSL, everything starts with explicit resource bindings, like at group 0, at bind 0.
You're mapping everything out.
You are explicitly telling the silicon exactly which memory buffers it has permission to read from and which buffers it is allowed to write to. By removing the guesswork, the GPU can optimize its memory bandwidth flawlessly.
It doesn't have to think, it just executes.
Exactly. This explicit mapping is the only way we can push hundreds of thousands of FFT calculations through the compute units without causing a traffic jam.
That makes a lot of sense. The strictness is the price of performance. So what does the actual architecture of this WebGPU pipeline look like for our Ocean? Walk me through the execution from the moment the user opens the web page.
It is structured as a multi-stage process. First, we have the initialization phase. The original Phillips spectrum, that static mathematical model mixed with the Gaussian noise, is computed just once.
Okay, just one take.
We usually run this on the GPU during the initial loading screen, and we store the resulting data in an immutable memory buffer.
That is efficient. There was no wind changing, so there's no need to recalculate the baseline probability every frame.
Precisely. Then the real-time render loop begins. Every single frame, we dispatch a WGSL compute shader. This is a special type of shader that does not draw pixels to the screen, it just crunches numbers.
Like a math workhorse.
Yes. This compute shader reads our initial spectrum buffer, applies the time phase using our dispersion relation, and executes the FFT algorithm.
And what exactly does this number-crunching compute shader spit out at the end of its run?
It writes data into 3 highly specific textures. First, the height map, which dictates the vertical y-axis displacement. Second, the displacement map, which stores the x and z horizontal choppiness we discussed.
And the third?
And third, the gradient map, which stores the normals.
The normals. The mathematically calculated direction that every single pixel of water is facing. Which brings us to the next massive challenge. We have geometry that is moving flawlessly, cresting and crashing with mathematical precision. But right now, without lighting, it just looks like a gray, undulating blanket of polygons.
It's pretty ugly without light.
It is time to paint this math with light.
Shading water is arguably as complex as moving it, because water does not have a single color. Its appearance is entirely dictated by its physical environment and the angle from which the camera observes it.
This brings us to a phenomenon you see every single day in the real world but probably don't know the technical name for: the Fresnel effect.
Exactly. Named after Augustin Jean Fresnel, it's a foundational principle of optics regarding dielectric materials like water or glass.
Right.
The Fresnel effect dictates the ratio of how much light is reflected off a surface versus how much light is refracted, meaning it passes through the surface. And it's based entirely on your viewing angle.
The math for true Fresnel is notoriously heavy, so we usually use Schlick's approximation in shaders, right? Something like 0.02 plus 0.98 times 1 minus the viewing angle to the 5th power.
Yes, Schlick's approximation is the industry standard because it is computationally cheap but visually indistinguishable from the real physics.
Let's translate that equation into what our eyes actually experience. If I am standing on a wooden dock looking straight down at my feet into a lake, my viewing angle relative to the water's surface normal is very steep.
And the approximation formula tells us that at a steep angle, the reflection coefficient is incredibly low, around 2%. That means 98% of the light passes through.
So it's basically see-through.
Exactly. The water acts transparent. You can see the rocks, the sand, and the fish at the bottom of the lake.
But if I lift my head and look out toward the horizon line of the lake,
your viewing angle becomes very shallow, approaching 90 degrees from the normal. The approximation formula shifts exponentially. The reflection coefficient shoots up near 100%.
So it stops being clear.
The water entirely stops being transparent and becomes a near-perfect mirror, reflecting the skybox, the clouds, and the setting sun. This dynamic shift between transparency and reflectivity based purely on the camera angle is the most vital detail for making water look like water, rather than blue plastic.
I understand the reflection part. We just sample a texture of the sky. But to make that looking straight down transparency work, we have to actually draw what is under the water. How do we handle that refraction seamlessly in a WebGPU pipeline?
It requires a classic rendering trick utilizing screen coordinates. Before we even begin to draw the water surface, we render the entire scene, the pool floor, the underwater walks, the sand, completely without any water present.
Okay, we render it dry.
We take that fully rendered frame and save it as a background texture in the GPU's memory.
So we have a hidden photograph of the dry world.
Exactly. Then, when we finally draw our water geometry in the fragment shader, we need to know what exact part of that hidden background texture to show through the water. We take the vertex's clip space efficient and we divide it by its W component.
The perspective divide. This converts the 3D math into 2D screen space.
Yes. That math gives us screen coordinates ranging from -1 to 1. We remap those to standard 0 to 1 UV coordinates. If we sample our background texture using those coordinates, the water acts like a perfectly clear sheet of glass.
But water is not flat glass. It ripples.
Right, so we take those UV coordinates and we distort them slightly, pushing them around based on the data in our gradient map, our normals. This gives us that beautiful, wavy, funhouse mirror, refracted look of objects sitting underwater.
Okay, here is where I get really excited about the visual fidelity. Because my absolute favorite part of looking at water, whether it's an ocean shallow or a swimming pool, is the underwater caustics.
Oh, they look amazing when done right.
Those bright, dancing, interlocking webs of light that sweep across the floor. Simulating that accurately seems impossible for a real-time game.
True. Physically accurate caustics require ray tracing billions of photons, bouncing them through the waves, and calculating where they land. It is computationally astronomical.
We can't do that at 60 FPS.
Not at all. However, Yongsoo's WebGPU implementation showcases a brilliant, highly optimized method for achieving this in real time.
Walk me through the trick. How do we fake billions of photons?
Instead of tracing individual photons, we utilize a 256 by 256 height field texture. We conceptualize a grid of light rays beaming down from the sun. As these rays hit our height field, we use Snell's law of refraction to calculate exactly how the angle of the wave bends each specific ray.
So the surface of the water is essentially acting like thousands of tiny, shifting magnifying glasses.
That is the perfect analogy. We then project overlapping triangles down onto the ocean floor based on where those bent rays land. But here is the true genius of the implementation. Inside the WGSL fragment shader, we utilize something called screen space derivatives.
Screen space derivatives. I know those allow the shader to look at what the neighboring pixels are doing. What are we calculating with them?
We are calculating the conservation of flux. We use the derivatives to measure the density of the light rays.
Density.
If a wave acts like a magnifying glass and bends a large cluster of light rays so they all converge and crash into a tiny single spot on the ocean floor, the derivatives detect that extreme compression.
And what does the shader do?
The shader responds by making that specific spot incredibly bright white. Conversely, if the wave bends the rays outward so they spread apart, the area is rendered dark.
So the math is literally mapping the physical density of the light rays to draw those sharp, bright, caustic webs dynamically. That is phenomenal.
It's a really elegant solution.
And what about God rays? Those thick, volumetric sunbeams that shoot through the murky water when you dive underneath.
Again, rendering true volumetric scattering, calculating light bouncing off particulate matter suspended in 3D space would destroy our frame rates. But we can fake it elegantly with a rendering trick.
Let me guess, more textures.
Exactly. Since we already have this highly detailed caustic texture calculated for the floor, we essentially slice it. We render multiple flat layers of this caustic texture suspended at various depths in the water volume.
Like stacking panes of printed glass.
Exactly. We pack these planes densely near the camera, and we use adaptive alpha blending to fade them together smoothly. As the camera moves, it creates the highly convincing parallax illusion of thick, 3D shafts of light penetrating the water, all without the devastating computational cost of a true volumetric fluid simulation.
It is all smoke and mirrors. Or, well, caustics and alpha blending. So we have built this stunning, perfectly lit, mathematically accurate ocean. It looks beautiful. But if we are building a video game, an ocean cannot just sit there looking pretty in a vacuum.
It has to be playable.
Exactly. It needs to react to the player. A boat needs to displace water and leave a wake. A cannonball needs to create a splash. How do we add local interactivity to this massive global FFT simulation?
Adding local perturbations interactivity is highly complex precisely because the FFT ocean is a global frequency-based simulation. You cannot easily just poke a single vertex in the frequency domain.
So what's the workaround?
We can layer completely separate effects on top of the final height map. For something simple and sudden, like a cannonball explosion, we use an analytical formula.
Something we just inject directly into the final vertex shader right before draws.
Yes. We can add a localized, mathematically defined ripple formula. Something like the initial intensity times an exponential decay factor multiplied by a cosine wave based on distance.
A decaying circle.
Right. It creates a perfect, decaying circular ripple radiating outward from the exact coordinate of the explosion. We simply add that resulting height value directly to the existing FFT wave height at that vertex.
That works for a quick splash. But what about something persistent and mechanically complex, like a large ship dragging its hull through the water, leaving a chaotic, foaming wake that persists for hundreds of meters? A simple decaying circle will not cut it.
For boat wakes, we have to escalate our methods. We use GPGPU dynamic displacement mapping.
GPGPU, general purpose computing on graphics processing units. So we're using the GPU to run an entirely separate simulation just for the boat.
Exactly right. We dedicate a small, localized texture, perhaps 512 by 512 pixels, that physically follows the coordinates of the boat. Inside this texture, we run a 2D fluid simulation, often utilizing cellular automata.
Let me stop you there. Cellular automata, like Conway's Game of Life, where pixels live or die based on their neighbors. How does that simulate fluid?
It is the exact same principle. The grid of pixels represents the water surface. Each pixel reads the height and velocity of its immediate neighbors. When the boat's hull pushes into the grid, it adds height and velocity to specific pixels.
And the rules take over.
Exactly. The cellular automata rules dictate how that energy transfers outward, pixel by pixel, simulating the physical displacement and the trailing vortices of the water being pushed aside. We calculate this wake simulation in real time, and then we take this localized wake texture and mathematically blend it directly into our global FFT height map right before the final render pass.
That is incredibly slick. It allows the global weather to affect the ocean, while the local physics affect the immediate area around the player.
Best of both worlds.
But I am looking at the sheer weight of this pipeline. We're layering FFTs, Fresnel approximations, Snell's law caustics, and cellular automata fluid dynamics. It sounds like an absolute recipe for 5 frames per second. How do graphics engineers optimize this pipeline so it actually runs on a standard consumer laptop?
Optimization is where the true rendering engineering happens. You cannot brute force this. Let's examine 3 major optimization techniques.
Okay, let's hear them.
First, distance blurring. As highlighted by the Babylon.js open source community, developers often try to hide the repetitive tiling of the ocean near the horizon by using expensive volumetric fog.
Which requires calculating depth for every pixel. That sounds heavy.
Right, it's costly.
Yeah.
Instead, you can simply blur the normal map of the water material directly inside the shader as the depth increases.
Just blur it out. Yeah.
As the water gets further away, the normals average out, the high-frequency chop disappears, and it achieves this moody, overcast, realistic horizon line with almost zero extra compute cost.
That is incredibly smart. It is an art fix for a math problem. What about the physical geometry itself? We can't possibly be rendering millions of highly tessellated vertices miles away from the camera.
No, we absolutely cannot. From the architectural breakdowns in GPU gems, we learn about using radial grids for level of detail, or LOD.
Radial grids, how do those work?
Instead of laying out a massive flat grid of squares, you create a mesh of concentric circles centered exactly on the camera's position. The mathematical formula for the radius of each ring is r equals an initial constant, plus another constant multiplied by the ring index raised to the 4th power.
Oh, I see the trick. Because the index is raised to the power of 4, the physical distance between the rings grows exponentially as you get further away from the center.
Exactly. You get massive tessellation, thousands of tiny, highly detailed triangles right up close to the camera where you can actually see the foam and the caustics. But as you look out toward the horizon, the polygons become massive, sparse triangles.
It's an illusion of infinite detail.
This radial grid moves with the camera, ensuring you have detail only where it matters. This technique allows you to render the ocean surface from 10 centimeters away all the way out to 40 kilometers without crashing the GPU's Vertex processor.
That is brilliant. And the third major optimization.
Dynamic branching inside the compute shader using frustum culling. The GPU processes vertices in massive parallel batches. We can utilize the frustum clip space, the invisible mathematical pyramid that defines the camera's actual field of view, to mathematically detect if a specific cluster of triangles is currently off-screen.
Meaning it is behind the player or just out of the camera's peripheral vision?
Right. If the math determines a triangle is outside the frustum, we use dynamic branching to tell the WGSL shader to immediately abort.
So it just stops calculating.
It completely skips the expensive FFT texture sampling, the Jacobian calculations, and the displacement MAC for those vertices. We literally only pay the computational tax for the water we can actually see on the monitor.
Okay, that covers the performance and the rendering side beautifully. But I have one final extreme edge case question for you. Everything we have discussed relies on a flat 2D grid moving up and down on the y-axis.
Yes.
What if my game is not set on a flat Earth? What if I am building a massive space exploration game, like Cosmos Journeyer, and I need this entire chaotic ocean simulation to wrap around a spherical planetary body?
Oh, that's a whole different beast. If you try to take our standard flat 2D FFT texture and map it onto a sphere using standard X and Z Cartesian coordinates, it will warp terribly.
The poles get pinched.
As the texture approaches the poles of the sphere, the math pinches. It will look like a twisted balloon. It completely ruins the illusion of a flowing ocean. To solve this, we abandon the 2D grid entirely and utilize triplanar mapping.
Triplanar mapping. I know this is used for texturing complex terrain like cliffs. How does it wrap an ocean?
Instead of looking down at the planet from the top and slapping a texture on it, you mathematically project the ocean FFT texture onto the sphere from 3 orthogonal axes simultaneously, the X, Y, and Z axes.
All 3 at once.
The shader blends the projections based on the direction the surface is facing, but more importantly for the physical waves, you have to completely abandon global y-axis displacement. You must use spherical coordinates, latitude, and longitude.
Right, because on a planet, the concept of up is relative. It's constantly changing depending on where you are standing.
Exactly. You use the latitude and longitude to calculate the orthogonal, tangent, and bitangent vectors at every single localized point on the sphere.
So when the wave moves,
When the FFT outputs a height value and tells you to displace a vertex to make a wave, you do not move it on the global y-axis. You displace it strictly along the normal of the sphere at that specific local coordinate. The waves literally push outward from the core of the planet, perfectly conforming to the curvature of the world, free of seams and pinching.
that is just. It's a staggering amount of mathematics, physics, and the silicon architecture all working in perfect harmony just to trick the human eye.
It really is one of the crowning achievements of real-time rendering.
So let's recap this monumental journey for the Bus and Sigma scholars tuning in. We started in 1802 with Gerstner's basic geometric circles to understand fluid motion. We upgraded to Tessendorf's statistical models, utilizing the Phillips spectrum, and Gaussian noise to inject natural chaos based on wind data.
A huge leap forward.
We learned how to animate that static probability field using the dispersion relation and how to crunch the massive ON squared mathematics in real time using the sheer algorithmic magic of the fast Fourier transform.
We then pulled those vertices sideways to create chaotic, stormy chop, utilizing the calculus of the Jacobian determinant to mathematically detect overlapping geometry and trigger dynamic foam.
Which was so cool.
And we moved all of this theory into the modern era, migrating from the clunky state machine of WebGL to the explicit, highly optimized memory bindings of WebGPU and strict WGSL compute shaders.
We painted that geometry with light, using Schlick's approximation for the Fresnel effect, utilized Green space perspective divides for refraction, and mapped the density of light rays using Snell's law and screen space derivatives to create real-time caustics. And finally, we optimized the entire pipeline with distance blurring, exponential radial grids, and frustum culling before wrapping the whole simulation around a planet using triplanar mapping. It is a monumental stack of technology.
It is a massive stack, but before we sign off, I want to leave you with one final, slightly provocative thought.
Ooh, I like those. Lay it on us.
We spent this entire deep dive utilizing the fast Fourier transform to decompose and reconstruct chaotic ocean waves using complex probability arrays and WGSL compute shaders. But the FFT and the compute architecture we just built is not just for rendering water.
Where are you going with this?
Yeah.
What else could we use this exact pipeline for?
Think about the underlying architecture. We are taking a spectrum of frequencies, applying phase shifts over time, and collapsing them into a physical state using massive parallel processing on the GPU. Couldn't this exact same WebGPU compute architecture be used to visualize quantum probability fields in real time for physics simulations?
Wait, really?
Or, going back to your digital audio workstation analogy, couldn't this entire pipeline be repurposed to manipulate and synthesize massive multi-channel spatial audio directly inside a 3D graphics engine, offloading the audio processing from the CPU entirely onto the GPU?
That would change everything about game audio.
The math of the ocean is fundamentally the math of frequencies and waves are the foundational language of the universe.
Whoa. From figuring out how to render a day at the beach to tapping into the mathematical fabric of the universe, that is an amazing place to leave it. To the scholars tuning in, thank you for taking this deep dive with us. Take these concepts, pull up a WebGPU playground, and go write some code. Push the hardware.
Have fun with it.
But remember, the next time you boot up a video game and you see a simple flat blue plane of water, well, you now know exactly what kind of chaotic mathematics are lurking just beneath the surface. Catch you next time.